everybody, I'm Greg Fishel. Voice got high there for a second. Welcome to bonus weather video number 1 for this week, and we're going to be taking a little bit of a deeper look at numerical models that are used for weather predictions, some of the history and the improvements and also the limitations that we still have. So let's go on ahead and miniaturize myself here, as I always do, and let's take a look at some of that history of numerical models to forecast the weather. Well, the first time it was done with computers was way back in 1950, and you can imagine that the computing power was not all that impressive back then. So by the time you actually ran the model to its conclusion, it was way after the amount of time that it would be useful. But at least we proved that this could be done, and we all knew that with advanced computing power that this would become better and better. 1966, a 6-level model, 6 vertical layers, was introduced, but it only covered the northern hemisphere, and the resolution was about 380 kilometers or 236 miles. So the grid boxes in this model were huge at that time. But again, it was the best thing that was available at that time. By 1990, an 18-level model with global resolution, not just one hemisphere, but both, had a resolution of 160 kilometers or 99 miles. So we're getting better, but it is still, very much looking at large scale things and not individual things like thunderstorms. Now, the European model runs at a resolution of 9 kilometers or 5.59 miles, and that's the resolution, and it has 137 vertical layers. So look back at that at number 2 there, where you had a 6-level model. Now you've got 137 levels or layers, if you will. The GFS is just slightly worse, but not much. 13-kilometer resolution or 8.08 miles and has 127 vertical layers. Now, there is a thing called the HER model, which stands for High Resolution Rapid Refresh, and this has new data feeding into it every hour and is updated every hour. It has a resolution of 3 kilometers or 1.86 miles. So this is really getting down to the small scale. Now, the average diameter of a thunderstorm is about 15 miles, okay? But models can only resolve features that are about 6 times the grid spacing. So if you take, 6 times 1.86, you're less than 12. And so the 3-kilometer resolution model can resolve individual thunderstorms, but the global models, if you take, like the 5.59 rounded up to 6 times 6 is 36, that's way bigger than the average size of a thunderstorm. So the global models cannot handle individual thunderstorms. So how do global models, or how do any model account for convection? Well, we know that force is equal to mass times acceleration, okay? And on the large scale, you can make this assumption where there is a balance between the pressure gradient force, which acts upward because the pressure decreases as you go up in the atmosphere. So a gradient always goes from high to low, and so the pressure gradient force is directed upward. Gravity is obviously directed downward, and so those two forces balance. So if the net force is 0, that means 0 is equal to mass times acceleration. Well, we know there's mass, right? I mean, there's air there. And so the only way the right side of the equation can equal 0 is if the acceleration is 0, okay? And that's the assumption on the large scale. But we know in thunderstorms, there are huge accelerations in the updraft. So obviously, we cannot use global models to explicitly forecast convection. So high-resolution models can handle these accelerations and resolve individual thunderstorms, but global models cannot. So how do they try to account for convection if they can't resolve individual thunderstorms? Well, it's something called convective parameterization, okay? And let's say we have a grid cell like this, okay? And so the model cannot resolve individual thunderstorms within that grid cell. And so what it does is it looks at different parameters. There are things like lifted index, which is the difference in temperature between an air parcel and the temperature at 500 millibars of the environment. There's something called CAPE, which is convective available potential energy. That's how buoyant the air is, and buoyancy is a force. And so it looks at all these different parameters and then estimates how much of that grid cell will be covered by thunderstorms. So let's say in this particular case, it thinks 25% of the box is going to be covered. So then it tries to estimate how much of the grid cell will be covered by convection and then account for the effects of that convection. Other things that it would want to look at is evaporative cooling. When rain falls into subsaturated air, there's evaporation that goes on and that cools the air. Or the latent heat of condensation. When raindrops actually form, that process leads to heat. And so it tries to account for all of these different effects. And in other words, it's making an estimate of how much of that grid cell is going to be covered. But, it's not going to be able to tell you individually, like if you're at this house, whether or not that's going to be affected or not. Because 25%, it isn't always going to be that upper left-hand corner, okay? It could be a little bit here, a little bit here, a little bit here, a little bit there. And so global models are not a good tool for forecasting individual thunderstorms. And even though these high-resolution models, can forecast explicitly, small-scale convection, the thing about it is that we are a long, long ways from being able to say that a thunderstorm here right now in 1 hour is going to be over this house. We're not even close to be able to do that. In fact, I had a colleague, for some of you old timers back in the 80s and early 90s, Bill Schmidt, and whenever a higher resolution model was introduced, he would say, oh, great, now we can have more detailed errors. And there's some truth to that. There really is. And so I don't know if in my lifetime we're going to get to the point where we can say that this thunderstorm is going to be over this house. Obviously, with increased computing power, that will get better, but I don't know that it's ever going to get good enough to be able to accomplish that goal, at least not in the short term. All right, folks, there are the credits. That is the bonus weather video for this Monday, the next one Wednesday, next daily weather update coming up tomorrow, and hope to see you then. So y'all take care, and we'll see you later.